Hey, welcome everyone to the second VTSS of this year. It's my pleasure to introduce our speaker today, Dennis Kristensen. He's joined by our guest panelist, Indy. The topic is simple and robust bias corrections. So, Dennis, the floor is yours.
Thank you very much. Thanks, Majid, and the other organizers for inviting me. It's a pleasure to be here. It's nice to be in my office. Nice to be virtually at the seminar. This is a paper with Martin Andreasen, who's at the University of Aarhus, and the title of the paper is Simple and Robust Bias Correction. And so the setup is the following. We take sort of some estimator, a given estimator, as a starting point, and this estimator could in principle come from anywhere. So maybe I should say here then that while this is a time series seminar, then the theory actually also covers sort of IRD data as a special case, but the applications we have in mind is in time series. So you should think about theta hat as coming from some time series model you fit it to a time series. Yeah. So for example, in like a VARM, vector autoregression or state space model or whatever. Those are sort of the application we have in mind. But at this stage, theta hat could really be anything. Well, it can't be anything because we require the estimator to be sufficiently regular in the sense that it satisfies sort of the usual first order. This distribution up to a first order is asymptotically normally distributed. So with cap T denoting the sample size, we sort of have as a high-level assumption this requirement that the estimator follows a normal distribution large samples with some large sample variance matrix sigma. And so with this result, and if we can come up with an estimator of sigma, say sigma hat, then we can sort of do standard inference. For example, we can compute t-statistics and then test simple hypotheses by comparing the t-statistic with critical values from the standard normal distribution. Okay, so this sigma hat, there's a large literature on how to obtain this sigma hat. There's many different ways of estimating sigma. In the econometrics literature, there tends to be a lot of focus on robustness. So, and when it comes to estimation of asymptotic variances or variances of estimators, this means that you want to come up with an estimator of sigma that imposes as weak as possible restrictions on the underlying DGP. So, for example, White came up with, in a linear regression setting, he came up with heteroscedasticity robust standard errors in a linear regression model. And then further, that was followed by sort of developing standard errors as also robust to autocorrelation in the standard errors. And a leading example of that is, for example, the New West sort of hack estimator, the heteroscedasticity and autocorrelation consistent standard errors. What should also be well known, hopefully, to you is then that these are just two particular estimators of sigma. There's many other estimators you could consider. When you have to choose between the different types of standard errors, you face a trade-off between robustness and efficiency. And so in general, you tend to find that if you want to have a very robust standard errors, you want to develop an estimator sigma hat that is consistent under as weak as possible restrictions on the data generating process, you'll have to give up on precision. So the more robust sigma hat is, so the bigger the class of DGPs for which sigma hat remains consistent, the smaller the precision is, the bigger the variance of sigma hat is. Yeah. And so as an example of that, suppose we have to choose between White standard errors and New West standard errors, then New and West are more robust because they also allow for autocorrelation in the errors. But that comes at a price in the sense that the New West standard errors converge with rate slower than root T, while White's heteroscedasticity robust standard errors converges with root T. So you sort of have to give up on precision to achieve higher level of robustness. Okay, so suppose you decide to go super robust, then sigma hat will tend to have a large sampling error in a given sample size, and that might then lead to sort of severe size distortions or lack of power when sample size is small. And so this has sort of led to a large literature on thinking about how to do inference when you're doing robust inference, with mostly focus on estimation of sigma. Okay, so this was just a bit of warm up. So here's then what this paper does. So in a sense, what this paper here attempts to do is pretty much like carrying out the same exercise as we had on the previous slide, but now with focus on bias instead of leading variance of the estimator. So we have in mind scenarios where you not just worry about the estimation of sigma, but you also worry about, you don't just worry about the quality of your estimator sigma hat, you also worry about the quality of your initial estimate of theta. In particular, you might worry about that theta hat has substantial biases in finite sample. And similarly to the way that a poor estimator of sigma hat might lead to poor inference, then a poor estimator of theta hat, where poor here means that it might suffer from large finite sample biases, will also lead to poor inference, lead to potentially severe size distortions and poor power performance. And so what we do here is then trying to sort of develop bias corrections, general bias correction methods. And what we propose is sort of a class of algorithms that sort of are bootstrap based, but at the same time actually computationally more efficient than the standard bootstrap. So we use bootstrap in the process, but in a different way than from what you might used to sort of when you think about when you generally think about bootstrap. In particularly, our proposed class of bias adjustments doesn't require you to repeatedly recompute the estimator on sort of new V samples from the model of interest. So it's computationally a lot faster than the standard bootstrap algorithm, but it's still simulation assisted. So the proposal is sort of very broad. It applies to pretty much any extremum estimator you could come up with. It's easy and simple in the sense that the proposal comes on almost closed form. It just involves estimating some population moments. And moreover, the proposal could also apply to to learn about other features of the distribution of theta hat. So the current paper focuses on how to use this algorithm to learn about the first order bias components of theta hat, but the proposal could also be adjusted or generalized to allow to learn about sort of, for example, higher order biases and higher order variances of the estimator. Okay, so as I said, for a given estimator, if you then want to apply our algorithm to a given estimator, then you, the researcher, has an option or a choice to make. You have to decide. So as I said, the estimator, the sort of algorithm takes as input a given bootstrap algorithm, a given V-sampling algorithm, V-sampling scheme. That's sort of the bootstrap part. You can then are free to choose which V-sampling scheme you want to use. And here, you should think about the V-sampling scheme as being connected to what are the underlying model you want to impose on the data. And so our V-sampling scheme can come in different forms. It can either be fully non-parametric, it can be semi-parametric, or fully parametric. And this choice here is then this brings us back to sort of the previous slide. This choice here then will reflect then how robust you want to be, how robust you want your bias correction to be. So if you want your bias adjustment to work for like fully general without imposing any restriction on the underlying TGP, then you want to go for the non-parametric V-sampling scheme. If you have some modest confidence in the model being estimated, then you can apply the semi-parametric version. And if you are sort of fully believe in your model that you're estimating, and so sort of have a fully parametric model, then you can apply sort of a fully parametric bootstrap scheme. So in this way here, sort of the bootstrap algorithm gives you sort of access to a menu of different bias corrections, and you can then choose the one which you, depending on how sort of risk averse you are to model misspecification, you can then choose more robust versions. These, on the other hand, the corresponding the resulting bias correction will, on the other hand, then be less precise compared to the less robust V-sampling scheme. So similar to the discussion on the previous slide, we here offer sort of a menu of different bias corrections where they come in different forms depending on how robust you want and how precise you want the resulting bias correction to be. So that's sort of the main idea of the paper and the proposal. Okay, so that's one sort of contribution of the paper. Another contribution of the paper is that we are sort of the first one to actually carry out sort of a comparative analysis of different bias adjustments. So we do this we do with bias adjustments with what people have done in the literature, talking about sort of the robustness precision trade-off between different standard errors. So I think, and this is sort of apparently not hasn't been done in the literature, sort of like think about how you can do bias correction depending on how much trust you have in the underlying model. So we seem to be the first one to actually point out that issue and also sort of carry out a theoretical analysis of this. So what we do sort of argue is, and here's the sort of maybe an even better connection to the initial sort of motivation talk about standard errors. So similar to sort of computational standard errors. So again, the standard error is sort of really much like an estimation of a variance or sort of a long-run variance. Interestingly, what we show is then that the leading bias term that you want to adjust for also involves long-run covariances of features of the model. And so similar to when you talk about estimation of standard errors, that is a quick question about how to estimate a potential long-run variance. Then similar when you want to estimate biases, then again you have to take a stand on how to estimate these long-run variances. And so similar to with standard errors, the covariances of these covariance terms that appears in the bias expression can be estimated in different ways. You can either choose robust estimators. These will give you a robust estimator of the bias, but on the other hand, they will tend to come with a bigger estimation error compared to the less robust estimators. Another sort of maybe insight that maybe has been ignored in the literature is then that if the chosen covariance estimator that you choose to implement the bias adjustment with does not replicate the sort of the autocorrelation structure in the data, then the bias adjustment will be inconsistent, and so you will not achieve higher order improvements by doing this bias adjustment. So similar to when you compute standard errors, if your data is autocorrelated, but your standard errors do not take into account this autocorrelation, then your standard errors will be incorrect. The same applies here. If there's autocorrelation in your data, but your bias adjustment do not take into this account, then your bias adjustment will be incorrect. So there's sort of a very strong sort of connection between thinking about estimation of standard errors and doing bias adjustment. And again, we seem to be the first one to point out this connection here. Okay, so here's like a quick literature review. The most closely related paper to what we're doing here is a paper by Yang in Journal of Econometrics 2015. So he proposed a particular algorithm which sort of coincides with one particular version of our general class of bias adjustment estimators. So we sort of propose a bigger menu of bias adjustments that includes his as a special case. And moreover, his implementation is actually not computationally efficient. And in some situation, exactly as I pointed out before, it might even be inconsistent. His estimator is not fully robust. And so in some scenarios, if you want to be fully robust, if you believe that, for example, there's a strong autocorrelation data, then Yang's estimator will fail to work. And so that's sort of probably the closest related paper. Other related papers is, of course, then the whole literature on bootstrap procedures. So our algorithm can take as input any bootstrap algorithm that you like. So for example, if you want to be fully robust, you might want to go for the block bootstrap in the implementation of a proposal. If you are willing to assume that data is a Markov process, then you can use the Markov bootstrap. If you're willing to assume that the model you have specified is correct up to the error distribution of your model, then you can use residual-based sort of bootstrap. And if your model is linear, you can sort of use sort of sieve-type bootstraps for the proposal. that's sort of the type of bootstraps that you can sort of combine with our proposal. Finally, and this sort of brings us back to sort of this discussion about efficiency versus robustness. There is actually a literature on efficient bootstrap, but that is only been developed for IRD data, and this was done by Brown and Newey back in 2002. So in a sense, you can think about this paper here, sort of in a sense, to some extent, like an extension of the ideas and results of that paper to allow for time series data with autocorrelation. There's also, but Brown and Newey doesn't talk about robustness. So this is, I guess, sort of the difference between Brown and Newey, that they sort of focus on efficiency given a particular DGP or particular assumption about the DGP. At the other end of the spectrum, you find a paper by Kleiner Santos that discuss robustness, but they talk about robustness of one particular bootstrap, namely the wild bootstrap. And so so you can think about what we do in this paper here, sort of then we sort of extend the Kleiner Santos analysis to talking about robustness of a broader range of different bootstrap algorithms. And again, with more focus on time series data with autocorrelation in it. So that's sort of the quick review of the literature. Okay, so let's then kind of start describing the proposal. So describing the proposal, I'll sort of follow the same steps as I did in introduction. I'll first talk about sort of like robust versus efficient standard errors, and then argue how that discussion also applies to robust versus efficient bias correction. And I'm going to do this through a very simple example, namely OLS in a linear regression model. So suppose we observe y and x over time. So we have yc and xc, these are observed. And suppose we want to regress y on x. So we're sort of looking at a linear regression model on the form here. Epsilon c is the error term, and we sort of impose the restriction that xt and epsilon c are stationary and mixing. Xt has the design matrix has full rank, and xt and epsilon c have zero contemporaneous, also sort of uncorrelated contemporaneously, but we do allow for time series autocorrelation in the two variables. But under these two requirements, then the OLS estimator, which takes this form here, is consistent. So a bit of notation. When I wrote E without a hat, that's the population expectation. When I write E hat, that's the sample expectation. So E hat of ZC for any given sequence of sets, then E hat of ZC is simply the sample average of ZC. So here's the OLS estimator. You should hopefully recognize this expression. That's the OLS estimator, He's a hat. And under the assumption we've made here, we know that the first order asymptotic normality will hold for this estimator. So it's root T consistent with root cap T consistent with cap T denotes the sample size, and is converged towards a normal distribution with mean zero, around theta naught is mean zero, with and variance sigma, where sigma has the usual sandwich form. The bun is sort of the expected value of xx prime, and the meat is the long run variance of xt times epsilon c. So a bit of another piece of notation, when I write v of a given random variable set, then that denotes the long run variance of that variable set. So here I choose here the variable set is xt times epsilon c. So v of xt epsilon c denotes the long run variance of that time series xt times epsilon c. Yeah. So this should be a well-known result from people who are sort of familiar with sort of standard basic time series econometrics. Yeah. Okay. So this is, so you can sort of see here that so now let's talk about sigma hat. If you now want to obtain an estimate of sigma hat, the bun is easily estimated. You just replace the population expectations by sample expectation. What's left for the estimation of sigma is then an estimator of this guy here, the long run variance of xt times epsilon c. Yeah. If you want to be fully robust and safeguard against potential autocorrelations, then you want to use heteroscedasticity and also correlation consistent estimator. And one such is the new West estimator I mentioned earlier. So that works as follows. You truncate the sum. So the sum here runs from 1 minus t to 1 minus cap t to cap t minus 1. You truncate the double sum at m. So you only sum from minus m to m, where m is chosen by u, which is sort of the so-called bandwidth. And then you sort of you only sum, and then you only sum over. Oops, that's so here. Of course, there should be there should be some hats here. So here, there's some hat missing. Epsilon c, you don't assume epsilon c. So of course, instead of epsilon c, you use the residuals. But up to that, then you compute the m first autocorrelations, and then you sum them up this way here. Yeah. So this is sort of a simple, this is sort of the standard approach for sort of autocorrelation robust inference in a linear regression. The problem with this estimator is that it sort of tends to be, it's not root T consistent. Even if you choose M, choose the sort of the bandwidth M optimally, then at best this estimator will converge at rate cap T to the power of 1/3. Yeah, meaning that in final samples, this can be a very noisy estimator of V. So this is a fully robust estimator. So this, if you plug this in to the expression for sigma, then you get a very robust estimator of sigma, but it's a very, but at the same time, in final samples, very noisy estimator. And so here's then the trade-off. You can now, if you're willing to assume that the errors are not autocorrelated, so the autocorrelation of xt epsilon c is 0, then you can simply instead use this estimator, and this is sort of White's heteroscedasticity robust standard errors. This is only consistent if your assumption of 0 autocorrelation is correct, but that comes with the gain that you now achieve root cap T consistency. If you're also willing to assume that there is actually no heteroscedasticity, then this third version, V hat 3, will work. Yeah. And this is even more precise than this guy here. So this you achieve again. So now you have two estimators that both root T consistent, but the asymptotic variance of this guy will be smaller than the asymptotic variance of V2. So you have the following ranking. The first one, the new West one, that's the most robust one. The third one is the less robust one. But in terms of precision, the ordering goes the other way. Yeah. So this is sort of the usual bias variance trade-off of robustness versus efficiency trade-off for estimation for standard errors. Okay, let's now then think about bias correction. And what you'll see is then that the discussion we just had for how to compute standard errors also applies to when you want to decide on how to do bias correction. So that remember just again, so if you're looking at the sampling error, the difference between theta hat, the OLS estimator, and theta not, then the sampling error can be written as this ratio of this sample average and this sample average. We're now interested in to learn about what is the mean of the left-hand side, what is the bias. So if we take expectations on both sides, then we should get the bias. But computing the mean of a ratio of two sample error, two sample averages is not easy. So what do? Well, we do the usual trick, we linearize. So we're now going to expand the right-hand side, the sampling error, around. So we're going to expand, in particular, we're going to expand the first term that appears in the denominator. We're going to expand that around the population expectation, population expectation of xt prime. Yeah. So you'll see now if you replace this e hat of xt prime with the population expectation, then you get this guy. So this is the ut here is the inference function of the OLS estimator. Yeah. So you have the population expectation of xt prime inverse times xt epsilon t prime. That's the inference function. So this is going to be the leading term in the expansion. And then we're going to have the first order term. That's going to be the adjustment for when we do the expansion around of e hat of xt prime around the e of xt prime. So we define vt as the difference between xc, xc prime, and its expectation. With these two definitions, if we now do a first order Taylor expansion, well, a second order Taylor expansion, then we get that this guy can be written as the sample average of the influence function times this guy here, the population expectation of xc, xc prime inverse, and then the product of the sample average of vt, which is sort of the expansion of the sample average of this guy relative to the population expectation of the same sequence. And then again, the sample average of the influence function uc. Yeah. So here you should keep in mind that both ut and vt are zero mean sequences. So this is a sample average of a zero mean sequence, and this is a sample average of a zero mean sequence. Yeah. So this is the expansion, and then we have a remainder term, which is sort of the second order term of the expansion. And given that, and given sort of standard results, you can easily show that the remainder term is of this order here. Yeah. So if we can now then take expectations at both sides, and then we ignore the higher order term, then you see then that by construction, ut as mean zero, as I said. So if you take expectation on both sides on this equation, then this guy goes out, and you're left with the expectation of the this second term here, this guy here. And you now see then that the expected value of the sample average of v times the sample average of u, that exactly gives you then the long run covariance between vt and ut. Yeah. So you see then that the bias of the OLS estimator, the leading bias of the OLS estimator, is simply this expression, 1 over cap t times the expected value of xt, xt prime inverse, times the long run covariance between vt and ut. The long run covariance appears as is simply the expected value of the product of these two guys, as you can easily check. Yeah. So this is sort of then an easy way to arrive at the leading bias of an OLS estimator in a sort of when we have when strict exogeneity of the regressors fail. Yeah. And importantly, you should now see then that the leading bias term again involves like a simple expectation of the regressors, and then a long run variance component. Well, in this case, a long run covariance component of xt and vt and ut. And so again, if you want to do bias adjustment, similar to if you want to compute standard errors, you now have to take a stand on how you estimate this long run covariance between the UT process, which is the influence function of the OLS estimator, and then the VT process, which is then the difference between the sample Hessian and the population Hessian of the estimator. If you give me an estimator V hat, then I will do bias correction this way. And then and this is sort of there, and then this is sort of the first main point of the paper. Different estimators of V will then lead to different estimators of the bias. The choice of V hat will then reflect your preferences for robustness versus efficiency, similar to we have different standard errors that are less robust or more robust. We can now develop different estimators of the biases, which are either more or less robust, depending on what you're willing to assume about the underlying features of the score function and the Hessian of the estimator of interest. Yeah, and so this is pretty much the paper in a nutshell. Okay, so this was sort of just a simple motivating example. Now let's then generalize the results to a general extremum estimator. So now let theta hat be some the minimizer of some sort of sample average, capital LC of theta, which takes this form here. This could, for example, be the OLS estimator, but could be any other extremum estimator too. We're going to impose enough regularity conditions similar to the OLS example. We now going to impose enough regularity conditions so theta hat is sort of root T consistent and converges towards a normal distribution. So we impose the usual condition that the score function is zero, that the Hessian of the estimator, the population Hessian of the estimator is non-singular. We're going to assume that the score, the first order, second order, and third order derivative of the sort of objective function that defines the estimator are stationary and geometrically mixing. and so on and so forth, to ensure that this convergence result holds. Yeah? We here focus on, in this scenario, we here focus on n estimators, but everything I say in the following does also apply to GMM estimators, except that sort of the expressions for the bias just gets way more complicated. But everything I say here, the ideas and the techniques that you're going to see now, also applies to GMM estimators with minor modifications. Okay, so this is a setup. So just to remind you, this LC is the objective function. Oh yeah, and piece of notation. If any function is evaluated at the data generating parameter value, then a suppressed dependence. So for example, the score function evaluated theta naught is denoted as nabla theta script LC. So this denotes the sort of score function evaluated theta naught. This denotes the second order derivative of the objective function evaluated theta naught, and this, of course, denotes the third order derivative of the objective function evaluated theta naught. Yeah. Okay, that's just a bit of notation. So here's then the first main result of the paper. Remember again, so let UT denote the inference function of the estimator. So that is the score function normalized by the population Hessian, inverse of that. And let VT be the sample Hessian normalized with respect to its expectation. So this is the generalized version of the UT and VT processes we saw in the OLS case. So these are just the general versions of that. Yeah. And here's then the result. Under the assumption as stated on the previous slide, then the extremum estimator will have satisfied this expansion. The leading term is the sample edges of the inference function. So this will follow a normal distribution, large samples with variance sigma, as stated on the previous slide. The second order term is then this B function of the sample average of the inference function and the sample average of the difference between the Hessian at time t and its expectation. And then we have a remainder term RT, which is of lower order than the first and second order term. Yeah, so we're going to ignore, so similar to the OLS example, we're going to ignore the higher order terms now, and then focus on the first and second order term. Yeah, the second order term takes this form. It's you normalize by the population Hessian, so this is a constant. And then inside your brackets, you have the product of the sample average of the VT process and the UT process. Yeah, so this is similar to the OLS estimator. And then you have a second term that didn't occur in the OLS example. And the reason why this doesn't occur in the OLS example is that this term involves the third order derivative of the objective function in the population. And this is 0 in the OLS example. But for nonlinear estimators, this term will appear, and this will then be a vector. This is sort of the vec operation of the product of the score function, the normalized score function, the sample average of the inference function with the self. Yeah. So this is sort of the expansion we're going to use. We now proceed similar to the OLS. Let's ignore the remainder term and then take expectation on both sides. Then this guy disappears because this is mean 0 by assumption or by definition. We ignore the RT term, and then we're left with expectation of the B term. Yeah, so that's that guy. Oops, there's a bit of mix here. Forget about the 1 over the 1 over t shouldn't be here. The 1 over t should actually be down here. So that's a typo here. Sorry. So the 1 over t should not occur here. It should occur down in the second line. Sorry for that. So that's a typo here. But other than that, the result are right. If we take expectation of B, then if we take expectation of B, then we get the long run covariance between the VT process and the UT process plus a half times the second order derivative of the objective function times the vec operator of the long run variance of the score function with itself. Yeah. And so here we have now, so you can sort of see here that the bias involves the long run covariance between the inference function and the d-mean Hessian process. and the lone run variance of the influence function with itself. Yeah. So again, if we want to do bias adjustment, we have to develop estimators of this lone run covariance and this lone run variance. Yeah. And so similar to when you want to do standard errors, you now have to take a stand on how you want to estimate these terms, and that involves a trade-off between efficiency and robustness. And so we're now going to talk about different ways of estimating these, and what you still see, each estimator maps back into a particular bootstrap algorithm. So there's a tight connection between the estimation of the bias connection, doing bias correction, and then doing bootstrapping of either the bias or other features of the model, as you'll see. Importantly, to be more precise, for given estimator V can be thought of as corresponding to a particular bootstrap algorithm, and a given estimator V will only be consistent if that bootstrap algorithm replicates the dependence structure in your data, in your DGP, in terms of the score and Hessian of the objective function defines the estimator. And so, for example, one example of a bootstrap algorithm that will fail to replicate any autocorrelation is, for example, the fixed regressor bootstrap. And so the fixed regressor bootstrap has actually been advocated to be used in time series applications. But you should not use this if you're interested in doing higher order refinements. Then the fixed regressor bootstrap will fail unless you are so lucky that either the regressors in your model are strictly exogenous, or the errors in your regression model have zero autocorrelation. Otherwise, the fixed regressor bootstrap will actually fail to do the job. And we conjecture actually also that the wild bootstrap will also suffer from the same thing. The wild bootstrap is widely used to do first order inference, but if you want to use it for higher order inference, then we conjecture that actually, again, similar to the fixed regressor bootstrap, that they will actually fail to do so. And this seems to be actually gone unnoticed in the literature. So while the wild bootstrap is very popular, it actually will most likely fail to deliver higher order refinements, which tends to be one of the first motivations for doing bootstrap in the first place, which sort of seems to then mean that the wild bootstrap is actually maybe doesn't really deliver what you might think it should do. How am I doing time-wise? I don't want to go over time. Let me just so it's another 20 minutes. Yeah, okay, so doing fine. Yes, all right. All right. So this, okay. So this is just so this is sort of the fully general expression of the bias correction for any given estimator. You should note here at this stage we have imposed minimal restriction on the underlying DGP. We haven't made any assumption about the score function or the Hessian, the score process UT, or the Hessian process VT, so that which comes from the first and second order derivative of the objective function. Just to remind you, this is UT, this is sort of the influence function, the V-scaled score function, and VT is the d-meaned Hessian of the objective function that defines the estimator. Yeah, just to remind you. So these are the definition of UT and VT. Yeah. So this stage we haven't made any assumption about UT and VT. All we've said is that UT and VT are stationary mixing, so that at least this lone run covariance is well defined, and this lone run covariance is well defined. So here's then the first step. If, as a researcher, you are willing to assume that the model is dynamically complete, in the sense that the score function is a martingale difference, then you can already sort of simplify the expression, this general expression, to some extent. You'll see then that when again VT, the lone run covariance between the score and the Hessian takes this form. If UT is a martingale difference, then half of these terms will drop out, because UT has conditional means zero conditional lags of VT. So that means that the first term simplifies to this half sum here. And moreover, the lone run covariance of UT itself collapses to be simply just the contemporaneous variance. So you can sort of see here then that if you're willing to assume that the model you're estimating is dynamically complete, then first of all, the bias expression simplifies, and there's a lot fewer terms that have to be estimated. So if you are willing to assume this assumption here, then you should use this expression here for estimation for bias correction, because this contains fewer terms to be estimated relative to the fully general form, which contains sort of 3 times t more terms to be estimated. Yeah. So here's already a sort of a considerable sort of simplification, which leads us to a bias expression, which is a lot, which can be estimated with much fewer errors involved. Yeah. So this is sort of the first main point to be made. And this is sort of then the second stage, you might then also be willing to assume that the Hessian function or Hessian process is a martingale difference. This is a lot stronger assumption. This will hold as long as the model, that the score function is a martingale difference. That was hold under the assumption that the model is dynamically complete. That the Hessian is a martingale difference. That's a lot stronger assumption, which would generally only be satisfied if data is IRD. So in other words, I would say this: you should only impose this restriction if you are willing to assume that that your data has 0 autocorrelation in it in the first place. It's meaning that data is IRD. If you're willing to assume that data is IRD, then or there's no autocorrelation in any function of your data, then your the bias expression simplifies to this expression. All the autocorrelation terms here also drops out, and you're left with this expression here. So this is sort of like 3 versions. So this is the fully general version of bias correction. This is sort of a semi-robust version that assumes the model is dynamically complete. But you should note here that you still need to do sort of long-run variance computation, because you still have these covariance terms to be estimated if you want to do bias correction. And if you are willing to assume that your data is IRD, then you have this simple expression here, and there's no long-run variances to be estimated. Everything, you simply have 4 sample moments to be estimated. The Hessian, the mean of VT, the variance, this is the variance of VT, the covariance between VT and UT, and the variance of UT with itself, and then the mean of the third order derivative. And so this version here can be estimated with root T consistency without further ado. So here, so if you have IRD data, it's quite easy to achieve sort of a fully robust bias correction, but that only which is root T consistent, but that estimator only works if data is IRD. So as I said, this paper here sort of in principle applies to both the results of this paper applies both to IRD data and time series data. But the interesting stuff really takes place when you allow for autocorrelation, because if you have IRD data, this is what you want to do. And this can be estimated with root T consistency and still be fully robust. If, on the other hand, you have a time series data and want to allow for autocorrelation, then you face the challenge that you have to do long-run variance estimation, even if the model is dynamically complete, because you do have to do estimation of this bit here. And the question is now, there you now face the choice, if you want to be fully robust, then you can no longer do root T consistent bias correction. As I said before, if you want to have a fully robust long-run variance estimator, then you will generally not achieve root T consistency. You will sort of, your estimator will have a slower than root T consistency. And so here with time series data, you do face a serious choice between precision and robustness. And so for the following, we're now going to focus on either this version here or this version here, both of which require sort of a long-run variance estimation. And then we're going to sort of have a sort of focus on how do different bootstrap schemes estimate long-run variances, and under what restrictions will these be consistent. So that's sort of the remains of the talk, really. So here's so we're going to focus, as I said, so even if the model is dynamically complete, you still have to at least estimate half the long-run variance covariance between the Hessian process and the score process. So then let's have a look at that guy in general. So let's just look at, so let's suppose we are in this scenario. You're not willing to assume that the model, so everything I said here also applies to this scenario where where UT is a martingale difference. But let's focus on the scenario where we sort of are not willing to impose this restriction, and we're looking at this guy here. Yeah. Okay. So in that scenario, we now have again. So this is sort of the long-run covariance between the score process and the Hessian process. That takes this form here. This variance depends on the underlying probability distribution of Vt and Ut, which we denote Pt. Yeah, so this is the probability distribution of the score and Hessian process. And in general, now the way you can think about the estimation of this guy can be done that you replace the population distribution by an estimator P star T. Not P hat T, because I'm here using the same notation as in the bootstrap literature. So you think about P star T here as an estimator of the population distribution of the underlying DGP, here expressed in terms of the score in Hessian. And so if we place PT in this population expression with P star T, then I get an estimator. At this stage, P star T is unspecified. So depending on which depending on which V-sampling procedure you use, you get different bootstrap algorithms, which in turn leads to different probability measures P star T. So this is sort of then the fully general estimator of V hat, which is then indexed by the particular choice of P star T. Yeah? If you use a very robust estimator of PT, then you get a very robust V hat. If you choose a less robust P star T, if you impose more restrictions on UT and VT and their distributions, then you get a less robust estimator of V. Yeah. We are now going to see that in some situations, these moments, for some choices P star T, these moments are not available on closed form, in which case you'll do use Monte Carlo procedures, which pretty much means that you sort of resample from the probability measure of interest, and then you sort of use those use samples to then compute the expectations under P star T. Yeah? You could also, anyway, so let me just skip this slide here. Okay, so this is pretty much our general procedure here. So you can sort of see here, then this is sort of, so this is our general bias correction method. We propose that you give us for any given choice of P star T that yields a given estimate of V hat T, which you can then plug in to the bias expression to do bias adjustment. Similarly, for this guy here, for any estimate of P star T, you can plug that into the own long-run variance of the score function, giving on this estimate of this guy, also an estimate of this and this, together with sort of standard estimators of these two moments. We then have an estimate of the bias, which we then use for bias correction. Yeah. So pretty much the game is, how do we estimate these two guys, which now you can see maps into which probability distribution do we want to choose, which estimated probability distribution do we want to use to describe or estimate the true probability distribution of the score and the Hessian processes. Yeah. Okay. Now let me just sort of talk about how our bias correction compares to existing proposals in literature. So there's an existing old literature on analytical bias adjustment. This pretty much involves like obtaining analytical expressions of the long-run covariance between the score and the Hessian process and the self-variance of the score function. These are sort of easy to implement once the analytical expressions have been achieved. And they come with zero simulation noise because no simulation are involved. But at the same time, they can be very difficult to derive. And even if they can't be derived, the derivations are very tedious. So to my knowledge, these sort of analytical bias adjustments are only feasible in linear models, as far as I know. Non-linear models, nobody have really been able to arrive at sort of analytical expression of the bias expression that I showed you on the previous slide. Another alternative is to do sort of jackknife for bias correction, but generally jackknife leads to sort of inefficient estimators. So even in an IID setting, is shown in Hahn, Huge, Kurstan, and Newey, that these actually using jackknife for bias correction comes with the resulting estimator has a larger variance than sort of alternative estimators of the bias, such as, for example, bootstrap bias correction or analytical bias correction. Then let me talk about bootstrap-based bias correction. So the usual way to do bootstrap bias correction is the following: that you, similar to what we propose, you choose some model for the DGP, and then you use that model to sort of generate data from the implied probability measure. That data you now use to sort of recompute your estimator, say CAP-S times, yeah, and then you take the mean of that the V-sampled estimators to get an estimator of the expected value of the original estimator, yeah. So this is sort of the way you normally do bootstrap bias correction. This version here is in a sense is better than our estimator, because this also will deliver also estimate higher order bias terms, while our estimator only will capture the leading first order bias term. So this will give you a more precise bias correction, but that comes with a severe computational cost. If theta hat is not on closed form, then this procedure involves solving CAP-S optimization problems, which can be very computationally costly. And from a theory perspective, as far as I know, then this sort of standard bootstrap procedure for bias correction, there's no theoretical guarantees that this actually works unless data is assumed to be M-dependent, or that the bootstrap model being used is fully parametric. So outside of that, there's actually no known results that using this procedure actually works in theory. In contrast, we are able to show that our procedure does deliver consistent bias correction, and in fact, we're actually able to show with which rate the bias correction works. And then finally, as I said, there's a paper by Yang who does something similar to us, but a restricted version. So again, here's to just remind you. So this is our general proposal for estimating long-run variances of, for example, the score in Hessian for given choice of a probability measure of VT and UT, leading to this expression. If these moments for the given choice of P star T, if these moments are not available, then we do standard bootstrap or Monte Carlo methods to replicate. We simply simulate VT and UT under the chosen probability measure, and then we compute averages of these of the simulated VTs and UTs to estimate, or well, to approximate the autocorrelation function of VT and UT under P star T. So in practice, you choose a model for the score and Hessian function. You simulate from that model the score and Hessian. Then you compute U and V. By definition, this is the U function, this is the V function. And given, so these here, you have stars everywhere to indicate that this is not the original sample. These are sort of new samples drawn from P star. And then given the simulated path of the score and Hessian, appropriately normalized, we can then compute autocorrelation function as we wish. Yeah? And then plug them back in to get V hat. Yeah? So this is how you would compute V hat if you can't compute the autocorrelation function of V and U under the chosen P star. Yeah? Okay, so I'm now going to discuss two versions of this, a very robust version and then a semi-robust version. So let's go look at the fully robust version. So one choice of P star is to use sort of like the block bootstrap. That is like one choice of P star. Here you sort of sample in blocks. So you you maintain the dependent structure of the original sample within the block, but then the blocks are mutually independent. So that's sort of the block bootstrap. If you now apply the block bootstrap and then feed that into the long-run covariance, what you get out, and this is a well-known result, you simply get the new West estimator. So in other words, if you use a block bootstrap for bias correction, then you pretty much that's equivalent to using the new West estimator for bias correction. Yeah. So
Dennis, so
yeah.
sorry to interrupt. Just 5 minutes.
Yes, yeah, I'm almost done here. So in other words, if you want to use the block bootstrap, sorry, yeah, so let me just hurry up. So I'm almost there. So you want to use the block bootstrap for bias correction, then that's a very robust bias correction, but it also delivers a bias an estimate of the bias adjustment, which at best achieves rate t to the power 1/3. So that's maybe not preferable. So this is sort of a very imprecise bias correction. And so an alternative, you can use the residual-based bootstrap. You then need to impose more structure on the model. So you now have to assume that the model comes with sort of that there is an error term in your model. So you have to impose more structure. So you assume that we now focus on models where data is generated by an autoregressive model, potentially of infinite order, and with an error term epsilon t. If we can compute the residuals from the model, then what we propose is then to resample the residuals as IID block shocks, and then feed those into the estimated model to then generate data. So this is sort of the algorithm. So this is like a residual-based bootstrap algorithm. And what we show then in the paper is then that this algorithm then leads to routine-consistent bias correction. So less robust bias correction, but on the other hand, more precise bias correction. And then I'm not going to have time to show you the simulation results, but not surprisingly, the simulation results shows you what you would expect. If you compare the block bootstrap for bias correction with the residual-based bootstrap for bias correction, then the block bootstrap is more robust. It delivers consistent bias correction, even if the model is misspecified. But in small samples, that bias correction can come with a fairly large variance. The residual-based bootstrap, on the other hand, only works if the model you're looking at is correctly specified up to the error distribution. But on the other hand, it delivers a more precise bias correction. So the resulting bias-corrected estimator comes with a smaller variance than the bias-corrected estimator using the block bootstrap. And so this is sort of, so it's a similar trade-off to when you do sort of, when you're sort of looking at sort of robust versus non-robust standard errors for infinite purposes. And so let me just wrap up. So what we do in this paper here is propose a general class of bootstrap-based procedures for bias adjustment. In some cases, the bootstrap version is on closed form. So for example, if you use a block bootstrap, then the bias correction pretty much just involves using computing sort of the long run covariances of the normalized score and Hessian of the extremum estimator using your West's estimator. And we then analyze these different bootstrap algorithms. You can choose your own bootstrap algorithm, and then leads to different bias adjustment components. What we haven't done, so what we have in the paper is just the bootstrap adjustment and the consistency of it. These are new results. What we are working on now, or would like to work on now, is in how to carry out inference after bias adjustment. How do we adjust inference, where ideally we would like to control for the fact that we now introduce additional noise in the estimator through the sort of random bias correction estimator. And we'd also then like to sort of extend the residual-based bootstrap algorithm to allow for regressors. And we'd also like to have some result on the wild bootstrap. As I said, we conjecture that the wild bootstrap will actually fail to deliver, deliver consistent bias adjustment unless you impose very strong assumption on the model. Yeah, I think that's about it. So let me stop here. Thank you. Oh, you're muted, Majid.